Okay, now I'm actually not going to use the PowerPoint as we go through this, because I'm going to teach it a little differently than how the other teachers might. Because this is how I teach it in AP, and to me it makes most sense. So we're just going to take, you'll still fill this in, but you'll just fill it in as I'm writing on the board. Okay? Okay, let's review really quick for some smiley faces. Can someone by raise of hand, did I hit play on that? Mm-hmm. Okay, good. One time last week, AP, I taught a whole lesson thinking I was recording myself, and I wasn't. Then I had to film the whole thing again to an empty classroom. So, don't want to do that. Okay, someone by raising hand remind us ionic bonding. Explain what's happening with the electrons in an ionic bond. Yeah, Taryn.
It's just like taking one from another.
Perfect.
So
So
like
it's
one has like one extra, one has like one less than extra.
I like how you said that. Yeah, so one takes one has an extra one, so they give, right? It's a transfer of electrons. How does my face fit in? How wide does my screen go, Clayton?
Like to the little fever cough sign, and then to like almost like I can see a little bit of that orange sign, just like a little sliver of it.
So like that?
Yeah.
I don't go past there?
Yeah.
Okay, perfect, thank you. Okay, someone else tell us what happens at the molecular level for our metallic bonding. Yeah, Jared.
They receive electrons and they go across all the different atoms.
Good. Yep, sea of electrons is the best way to visualize it. All right, they're just flowing throughout the entire thing. Once again, is why they're such good conductors of electricity. They're very malleable, so on and so forth. Good. Jeremiah, what's my face for that? Okay, someone else tell us what's happening at the molecular level for covalent.
Aren't they sharing electrons?
Good. That's my face, Josh. So this is where they share. Okay, and this is what we're learning how to draw in this unit, or how things share and what their molecules look like. Okay, ionics, we've already seen pictures. The reason why we're not going to learn how to draw them is because they're just always that positive, negative, positive, negative, positive, negative, big magnet thing, right? This is just that sea of electrons, but when you share, there's a lot of different combinations and ways in which they can build. And so that's what we're learning how to draw. So the things that we're learning how to draw today are known as Lewis, actually let me write this over here, Lewis structures. Okay, Lewis structures are a picture, a 2D picture of how atoms are bonded to each other. So that first blank right there where it says they are designated to show the placements of valence electrons in molecules and how those valence electrons are being shared. Okay, so step one, so just write this on that blank, is we're going to determine the number of valence electrons. Okay, so our first step is we've got to know how many electrons they each have individually to then know how they're going to share. Okay, if the formula carries a charge, there's your next blank right there. So if the formula has a charge, that means you either have a bonus electron or you've lost some electrons, depending on what the charge is. So if something has a negative charge, what does that tell me about electrons? It has more. Yep. So a negative charge means you add electrons. And a positive charge means that you subtract electrons. So careful on that because mathematically it feels a little backwards, right? That positive is you're taking away, negative means you're adding, but it's all because of the charge that electrons have, right? They're negatively charged things. Okay, so let's look at, I think the example we're going to carry through our steps is SO4 2 minus. So what we want to do is know the valence electrons for each of the pieces in there, okay? So let's start with sulfur. So how many electrons does sulfur have for valence? 6. Good. Can someone remind us how we find that number? Good. I see a lot of us going like this, right? We count the columns, skipping the D block, right? And in this case, since they're only covalent, you're never going to be asked a metal, right? Because metals are covalently bonded, okay? Okay, oxygen has also 6. Okay. Now, that -2 tells me what? That there's a bonus 2 going to be added in our picture. So we want to make sure we don't forget that. Okay, so when you're counting them all up, make sure we don't lose track of that. Okay, step 1, how many valence electrons everything has? Step 2, okay, is we are going to make what is known as the skeleton for our molecule, which is where we place the first element in the middle and then all the others around it. So we're going to build what's known as the skeleton. Where the first element listed goes in the middle. Okay, so for example, and then we'll talk about the exception. Okay, so in that box right there for SO4 2 minus, sorry, I'll give you a second to keep writing. So this is my formula. So that means sulfur's in the middle and there are 4 oxygens around it. So my skeleton would look like this. I have S and then 4 O's. And we always just place them just for make it uniform. Either it's always top and bottom, left and right. We don't really place them at diagonals. So that's what this skeleton looks like. Questions on that step? Now there's one element that can never go in the middle of a molecule. Any guesses of what that would be? Oh, I heard it whisper over there. It's hydrogen. Hydrogen can't be in the middle. Why would that be? Why can't hydrogen ever go in the middle? He's too small. He can't bond that many times. He, she, whatever it is. But it's too small to bond more than once. Okay? Now, before we go to the next step, let's just review really quick here. Can someone remind us, why do atoms bond in the first place? Like, why don't they just stay as individual Legos? What causes these Legos to stack? So the whole reason why things bond in the first place is because they're trying to achieve a full outside shell. When they have a full outside shell, it makes them stable. And why that is, scientists maybe don't know. They've just discovered that's what happens. That if something doesn't have a full shell, then it's prone to either grab or share to get a full shell. Okay? Now keep in mind that the noble gas family is the family that is full. And so often they don't bond very often, but we'll see that sometimes they do. And we'll talk about that why in a second, okay? Okay, so step 3, so step 1, valence. Step 2, skeleton. Oh, sorry, I forgot something with our skeleton. We gotta add the valence to our skeleton, okay? So sulfur has 6, so I'm gonna place 6 dots around sulfur. And then 6 dots around each of my oxygens. Now, if you are not a pencil user, most of you are, I would maybe recommend it for this type of thing because the first time you draw your picture, it can look a little messy. And so then normally you'll want to like kind of clean it up. Or you just can redraw it after. It's up to you. But okay, so skeleton, step 1. Now keep in mind at some point we will add those bonus 2 still. Do we want to add it in step 2? Yeah, let's add it to step 2. So where we're gonna add the bonus is we're gonna add these to one of the outside atoms, making sure they don't get overfilled though. Okay? I'm gonna do mine in a different color just so we can remember where they came from. Okay? So my bonus 2 dots, I'm gonna do in green. So it doesn't matter which one we add it to, just making sure you don't fill it past 8. So I'm gonna add 1 here, and we'll add 1 here. But you could have added it to this one or that one, but I wouldn't add them both to a single one because then that oxygen would have 8. And if it has 8 already, then it's not normally gonna bond with things, so. Okay, going back to step 3. So step 3 is now we are going to draw the bonds. To make them all stable. Okay, 2 things to note with this. Number 1, each bond is 2 electrons. Because the way it worked with the sharing is it says, okay, I'll share one with you, you share one with me, and we'll create a bond. But they both have to give in that case. Okay? The second thing is that the outside atoms can't have more than 8 total electrons. So once they have 8, they stop bonding. Okay, so let's redraw our skeleton. We did these in steps just so it'll be easier when you go back. Like remind yourself, sometimes if you just have the complete picture, it's hard to remember. So let's redraw our skeleton over here. 4, 5, 6. Oh, that's not an S. 1, 2, 3, 4, 5, 6. 5, 6. 5, 6, and then we added bonus ones. There and there. Okay, everyone ready to draw some bonds? So to create the bond, it's I'll share with you, you share with me. So oxygen has 1 here. Connect a dot to a dot. There's a bond. Now notice that once I do that, that bond counts for both, and it counts as 2. So I'm just going to circle so we can count here. That because oxygen now has 1 or 2, 4, 6, 8 electrons. He is done. He's happy. Don't bond anymore. Okay. All right, continuing on. Okay, same thing here. Let's draw another bond. So dot to dot. Do I need to bond any more in that case? Nope, because check. 2, 4, 6, 8. He's done. Okay, coming down here, same thing, connect dot to dot. But what's going on with that oxygen? Good, he's still lacking, right? If you count, he's only up to 7. So now what's going to happen is he's going to form what's known as a double bond, where it's going to share again. So I'm going to move, this is where having a pencil is helpful. So this little dot that's up top, just to make it clear, I'm going to move it down here. And then I'm going to move that dot just to make a straight line, like so. Okay, check your count. 2, 4, 6, 8. He's happy. Coming over here, do one line. Once again, still lacking. Draw a second line. Check your count. 2, 4, 6, 8. Questions on step 3 for drawing the bonds. Yeah.
Does it not matter if sulfur has more than 8?
Good question. No, it doesn't. So notice that right here, it's only the outside ones that can't have more than 8. The inner one can have more than 8. Now there is a rule in a sense of some molecules can't, but that means the molecule wouldn't exist. And if it doesn't exist, I'm not going to make you draw it. But just to clarify, is all the elements on row 2, those ones can't ever go past 8 no matter what. If they're in the middle or outside, it doesn't happen. But the reason why I know that this happens is because if I don't draw those other lines, do your oxygens have what they need? No. And if they don't have what, if the outside ones don't have what they need, then it can't go past 8. Does that answer your question? Yeah, great question. But yeah, you're totally right. If you check sulfur, 2, 4, 6, 8, 10, 12 are around the middle. So sometimes when you first learn, like sometimes you'll learn how to draw these structures like in 8th grade and things like that. They often introduce this thing known as the octet rule. It's not so much as a hard rule as it is like a guideline, where yes, it's generally 8, but the reason why is the D block allows atoms to go past 8. If you remember when we talked about the hotel and how many electrons can dwell on each floor of the hotel, we look at these black numbers, the 3rd floor of the hotel can actually hold up to 18 electrons. So that's why sulfur can go past 8. So, great question. Okay, any others right now? Okay, step 4. Step 4 actually is kind of what we just did, but I want to write it down as a step so you don't forget. Is check your outside atoms for an octet. Okay, now the octet can be either just some terms here to be familiar with. We call the dots that aren't bonded, those are called lone pairs. And it's a pair of electrons that's lone because they're not being shared. And then the bonded ones we call just the bond. So when we add up the 8, it's just, it can be a combination of lone pairs and bond pairs, but it just has to be 8 total. If you want to redraw it, you can, but pretty much it's what we just did. So just remember that you check and make sure they all have 8. If something doesn't have 8, then you might need to rethink what you've done. In particular, a lot of times is, did you miss any bonus electrons? So if we didn't add those on, it wouldn't have worked out very well. So, questions on checking your octet? Okay, now notice one thing. I only can use what I have. If I'm lacking, I can't just add more or less. Hi.
Hello?
Box. Oh, I was like, I don't even know what it said. Do you want to take the box? Or sign first? That's fine. Thank you. Okay, and then step 5 is what we call our finishing step, where it's just adding the last fine details. Okay, so step 5 is 2 things if it's necessary. So step 5 is we add brackets and charge if it has one. If something didn't have a charge, you wouldn't have to do step 5. But whenever something has a charge, the final thing that you do, I draw right here, can you still see that, everybody? Is that too low, Tanner?
That's good.
Okay, so here's my final picture. I'm just gonna redraw it in our new box here. Okay, is the final step is you put brackets around the picture if it has a charge, and then the charge goes outside. Once again, if something didn't have a charge, you don't have to do that step. But if it has a charge in the formula, then you've got to end it by showing a charge on the molecule still. Questions so far before we just keep practicing? Yeah, sure.
For step 4, it says there is an exception note.
Oh, thank you. Thank you. Okay, there's one atom that doesn't want 8. And that's hydrogen again. Because for hydrogen, how many electrons can the first shell hold? Only 2. So hydrogen only needs 2. You can also keep in mind hydrogen only has 1 to give, right? So it doesn't really have another place to share again. But meaning you should never have a double bond with hydrogen ever, because otherwise it doesn't make sense. There are such things also as triple bonds. Those exist. So if it's not bonded and needs more, you can bond 3 times. There is no such thing though as a quadruple bond. So if you find yourself making a quadruple bond, we need to backtrack a little bit. So, okay, last note, and then we'll do some more practice here, is this thing known as resonance. Let me check your blanks here. So one thing you might notice with this picture, okay, is you might have drawn it, I mean, you probably drew it like me because I showed you, but if you were to do it by yourself, you may have drawn it where the double bond was like here and here, or here and here, right? Just in different spots, but it looks pretty much the same. The idea of when you can have a double bond that can be in multiple places, but the molecule still satisfies the rules, is what it is in a sense it's a molecule that resonates. Does anyone know what the word resonate means, like when you refer to it in music? If something is resonating, you resonate a note. Or like a string. What's a pitch, like if a string were to resonate, what would the string be doing? There you go, right? It's vibrating, it's another word for that. So the idea of a resonant structure is that molecules' electrons aren't stagnant, right? Next time not next time, the time after that, we're gonna build these structures with some Play-Doh and toothpicks. But bonds aren't really like toothpicks. They can move and they can change. So a resonant structure is a structure in which things can change and move. So, is everyone okay if I erase this real quick? Everyone got the rules down? Okay. So you have another example, I think already, of ozone, O3. Where after drying it, some people would end up with a picture like this, and others would end up with a picture like this. A lot of times with resonance, it's kind of like, well, they just like mirror images of each other, and the answer to which structure is correct is both. Because the molecule isn't this, it's not this, but it's actually a perfect blend of both. So in chemistry, the way that we designate that on our answers is we actually draw all the options with this double-headed arrow in between them. So here's your first blank. So some molecules with double bonds, so it only happens when you have a double bond, can't be represented by a single Lewis structure. Okay, the actual structure is an average of all the possibilities. Because the electrons are distributed evenly between both sides. Now the way scientists actually know this is pretty cool. Scientists have a way to measure the length of bonds. It's a little bit more technical than taking a little tiny ruler up to it, but you can pretend that's what they do. Okay, what scientists discovered and how they determined resonance is they found that when they measured ozone, okay, so when they measured the length of this and the length of that, they found they were equal in length. But the length was longer than it's longer than a double bond, but shorter than a single bond. So these resonance structures kind of create these like half-ish bond lengths, which is where it comes from. And so that last blank right there is, you know the blank? Did I miss one?
Show blank possible structures.
Show all possible structures with a double-headed arrow. Now, I'm going to give you Mrs. Alviso's shortcut for resonance. Maybe one day I'll petition for it to become a real thing. It's a little tedious, in my opinion, and takes up a lot of space to draw multiple structures for an answer when really you're drawing the same thing, just moving it around, right? So in this class, I'm okay if, let's say, a question was ozone. Instead of drawing both of the pictures on your answer, if you want to just draw one picture, but then put that arrow underneath it and tell me how many different pictures you can draw, you don't have to draw both pictures. That's like my shortcut that I'm okay if you use. Because to me, you tell me it's resonating, you know what it's going to do, I don't need you to draw both pictures. So, and we'll show an example of that here in a second. So, okay, any questions? Okay, let's do, I want you to try, the first one's pretty straightforward, so I want you to try with maybe someone nearish by you, okay? Try making the Lewis structure for CF4. Ready, set, go. And then we'll check it here in a second.
C is in the middle. There's no natural electrons, and so there's 4 less.
when you're done, set your pencil down. Now, it's up to you. The point of the two boxes, like the work box and the Lewis structure box, is if you like want to draw it in the work box and then make a cleaner picture if you're not using a pencil, but you don't have to use that work box. It's just there if you need it. Looking good.
What does it want to know by like,
Oh, I'll explain those things in a second. Some of them actually, you don't even have to do. It's just the way the other teachers teach it, you use those, but you don't really need them. So, okay. Everyone ready to go over it, and then I'll kind of explain those other boxes. Okay, you should have, so you should have put carbon in the middle. Carbon comes with 4 valence electrons. Fluorine, there's 4 of them. And they each come with 7. Okay, and so then bond, and you're done. If you have a picture like that on your paper, go ahead and give yourself a smiley face. Okay, now once again, these other things are just there to kind of help guide. The only one that I really care about, so you can just cross these 3 off. We're not gonna worry about counting those. But I do want you to make sure, so the tally check is to make sure you did the right number of valence electrons. So we did that. And then the octet check is to make sure all the outsides have their 8. Right, so 2, 4, 6, oh I forgot to draw one on that one. 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Check, we're done. If this isn't true, then you probably did something wrong. So, okay, let's try the next one. Put that one up there. Let's try the next 2. And then we'll do SO2 2- together as one more practice. Okay, so try NH3 and try H2S. When you're done with those 2, go ahead and set your pencil down. Oh, never mind, continue. Those are just your counts.
Yeah.
Those aren't in your picture.
Yeah.
Keep going, you're doing great. There you go, that's what I'm about to say, good count, Riley.
so, I should know if it's something.
Yes. Yep, very good. Why?
Just because that windows right there, like that windows have to go on the outside.
Good, and the other reason is, remember, hydrogen can't ever go in the middle.
Oh.
So, but you are right, yep, so put S in the middle. do NH3 on the board. It looks like as I walked around, everything looked good. It's just a double check. So nitrogen has 1, 2, 3, 4, 5. Got 3 hydrogens around it. They each come with 1 bond, bond, bond. Check your octets. Is hydrogen satisfied with its octet? Yes, it's not technically 8, but that's all it needs, right, is only 2. So those are all good, and nitrogen looks good. And we're done. Okay, your SH2S picture should look like this. And once again, where you placed your H's doesn't matter, but you should have single bonds on both sides and then 2 sets of lone pairs on the middle. Questions? Okay, show me your little rating here just so I can see. On your hand, on a scale of 1 to 5, 5 being like, I'm ready for the homework, 1 being like, I need more help. And then you can go somewhere in between. Okay, sweet. Okay, we're just gonna do one more so I can show you resonance one more time, and then we won't even do the rest of the problems, and we'll just let you practice, and then as you need help, I can come around and help you. Okay, so let's do SO2 2- together. Okay. So step 1, figure out how many valence electrons each of these have. They all have 6. Okay, so we're going to draw our skeleton. So we have S in the middle, O's on the outside. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, sulfur. 1, 2, 3, 4, 5, 6. Now in this case though, we don't want to forget, what does the 2- mean? 2 extra. So we're just going to add 2 extra electrons to the outside atoms. Okay, so we go here and here. Actually, can I change something I said earlier? I think this will make more sense moving forward. Save your bonus electrons till the end. And then place them where you need them. Okay? Okay, so we're going to start by bonding. Yeah, let's do that. Okay, so we're going to do, we know everything has to bond once because it's at least, you know, there. Actually, erase. We'll do what I said before. It should work out. Put those dots back. Okay, bond the other side. Do I need anything else? Check your octets. 2, 4, 6, 8. 2, 4, 6, 8. I'm just going to move this dot down here. Typically our dots come in pairs, so if they're not, kind of move them around so they're grouped together. But there's your picture. Sorry, I picked a bad one. That one doesn't resonate. Let's see if I have another resonance one on here. Okay, let's skip to SO3 really quick. That was the one I wanted to do. Oh, I am missing something on my picture. Brackets. And 2-. Okay, let's do SO3. Okay, so we got S in the middle with 6. 1, 2, 3, 4, 5, 6. Oxygen with 1, 2, 3, 4, 5, 6. 1, 2, 3, their dots placed. Okay, let's go ahead and bond where we need. Okay, so connect the dot. Does oxygen have its octet yet? Not yet, so we're gonna bond again. I'm gonna move it over here, these two, just to make them, once again, cleaner looking, so the lines aren't kind of all over the place. Okay, this one, same thing, so I'm gonna need to bond twice to get oxygen, it's 8. This side, we'll also need to bond twice to get oxygen, it's 8. Just pair up those electrons. Now, can this resonate? It has double bonds, does it resonate? Give me a thumbs up if you think yes, thumbs down if you think no. Let's just kind of check and see if we understand what resonance means. So the answer is actually no, it doesn't. So why can't this resonate? What did we say happens to the electrons when they resonate? It means that they're moving somewhere else. Does this bond have anywhere else to move to? No, because there's a double bond here and a double bond there. So that doesn't resonate. It only would resonate if, hypothetically, let's just say that was a single bond instead. Then the structure could resonate. Because you could, and there'd obviously be extra electrons on that one, right? It could be in more than one place. But all double bonds don't mean resonance. Resonance is just think, okay, could I draw this another way and it still work out, but look a little different? Then it resonates. If it's gonna look the same no matter how many times you draw it, it can't resonate. Okay, any general questions for now? Okay, let me give you your homework assignment. So we're not gonna worry about doing the other ones in the notes if we feel good. We might as well get started on this. Okay, so this is your homework for tonight. The goal would be, let's finish it up in class. And then you can ask me whatever questions you need. I will post an answer key to